plot for a unity feedback system which is characterized by the open loop transfer function 200 s plus 2 upon s square plus 10s plus 100. So let's try to solve this problem. Now first we will have to put s equals to j omega in this transfer function so that we can obtain gj omega. Let us first simplify this transfer function. So we will have gs equals to, we can take 2 as common, so we are left with 1 plus s by 2 here, and we can take 100 as common from the denominator, so we are left with 200, 1 plus s by 2 into 2 upon, this is s, this will be s square upon 100 plus 10 upon 100 s plus 1 into 100. So this will be, zeros will be cancelled, and 2 into 2, so it will be 4. So gs equals to 4, 1 plus s by 2, so it will become 0.5 s, so 0.5 s upon, this is s square by 100, so we can write it as s by 10 square plus, this is 10 upon 100, so it will become s by 10, and this is plus 1. Okay. Now we will put s equals to j omega in this. So gj omega will be equal to 4, 1 plus 0.5 j omega. This will be j omega square. So it will be j square omega square. Now we can write it in this way, 4, 1 plus 0.5 j omega Now this is j square omega square. So j square is equals to minus 1. So this will become minus of omega square by 10, or we can say minus omega square by 100. Okay. So we will have gj omega equals to 4, 1 plus 0.5 j omega upon, this will be 1 minus omega square by 100 plus, this is j omega by 10. So we have obtained gj omega here. Now we are going to take the magnitude of this and then logarithm of magnitude. Okay. So first magnitude will be written and then 20 log of m we have to calculate. So I am writing here 20 log of gj omega. This term, it is the magnitude of this transfer function. Okay. So we will write here 20 log, first term is 4, so 20 log of 4 plus 20 log of this term, the magnitude of this term, that is 1 plus 0.5 omega j omega. Then this term, because it is in denominator, so we will write minus sign, minus 20 log of j omega magnitude, then minus 20 log of this whole term magnitude. So we will write 1 minus omega square by 100 plus j omega by 10. So this is 20 log of the magnitude of gj omega. Now we are going to write it in the most simplified way, that is we are going to write the magnitude here So this will be 20 log of Gj omega, 20 log 4 plus 20 log magnitude of 1 plus 0.5 j omega. So it will be under root of 1 plus 0.5 omega square. Then minus 20 log of omega square. Okay, this will be the imaginary part is omega and real part is 0. So under root of omega square. So we will write omega here. Then we have minus 20 log of under root of square of the imaginary part and the real part. So minus 20 log of under root. The real part is minus 1 minus omega square by 100. Okay, so what we have done, we have calculated the magnitude and then 20 log of the magnitude we have calculated and then we just simplified it. Okay, now for the magnitude plot we have to form a table in which we will consider each of these factors and then we will make a comment about these factors, that how they can be represented in the Bode plot. Okay, so let's form a table here. So our first factor is 20 log 4, which is a constant term. So we will write here 20 log 4. Now when we calculate this 20 log 4, it will come out to be 12 dBs. Okay, so this factor is having the magnitude 12 dBs. Then corner frequency for the constant term, it is 0. So we will write here none. Okay, no corner frequency is there. Then slope for a constant term is always 0 dBs per decade. Then remarks. So this constant term, how it is going to be represented on the Bode plot? It will be a straight line which will start from the point 12 dBs and it will have the slope 0 dBs per decade. So here we will write it is a straight line. Okay, so this was our first factor. Now second factor we have, it is the term 20 log under root of 1 plus 0.5 omega square. So we will write it here, that is 20 log under root of 1 plus 0.5 omega square. Now corner frequency will be, this is omega t, so t is equals to 0.5 and corner frequency it is equal to 1 by t. So t is 0.5, so 1 upon 0.5 it will be 2. So corner frequency will be 2 radians per second. Slope, because this term it is present in the numerator part of the transfer function and here we are having 20, so its slope will be plus 20 dBs per decade. So now this factor will be represented on the Bode plot by a straight line which is having slope 20 dBs per decade and it will start from the corner frequency, that is omega equals to 2. Now let's come to our third and the fourth factor. So our third factor in the magnitude equation is minus 20 log omega. So we will write here minus 20 log omega. Corner frequency will be 0 for it because it is due to an integral factor 1 by s. So corner frequency is 0, that is none. And slope will be minus 20 dBs per decade. Now how this factor is represented, it will be a straight line which will have the slope minus 20 dB per decade, and it will pass from the frequency omega equals to 1. So we will write here now come our fourth factor. So fourth factor is this term minus 20 log under root of 1 minus omega square by 100 plus omega by 10 square. Now corner frequency will be, here we will have omega equals to 1 by t, and t is here 1 by 10. So our corner frequency will be 10 radians per second. Slope due to this will be minus 40 dBs per decade because this is a quadratic factor. Here we have a quadratic term. So this will be minus 40 dBs per decade. This is the second order term here. So we will have the slope as minus 40 dBs per decade. Then how this factor is going to be represented? It will be a straight line which is having slope minus 40 dB per decade, and it will start from the corner frequency omega equals to 10. So here we will write so for all these four factors, we have made the remarks that how these factors are going to be represented on the Bode plot. Now comes the phase plot, because the Bode plot, it is both magnitude and the phase plot versus the frequency. So now we are going to calculate the phase angle of the transfer function. So our transfer function was gj omega. This is our transfer function. Here we have 4, 1 plus 0.5 j omega and this. So we will first calculate its phase angle, that is phi. So for this term we will have tan inverse of 0 upon 4 because imaginary part is 0 here and real part is 4. So its phase angle will be tan inverse of 0 upon 4 minus we have this tan inverse of omega, this 0.5 omega upon 1. So we will write minus tan inverse of 0.5 omega upon 1. Then due to this we will have tan inverse of omega upon 0 because imaginary term is present but real part is 0. So we will have minus tan inverse of omega upon 0. Then we will have this term. So real part is this and imaginary part is this. So we will write minus tan inverse of imaginary part is omega by 10 and real part is 1 minus omega square by 100. Now we will simplify this. This is 0.5 omega upon 1. So it can be written as omega upon 2. Okay. So we will have phi equals to tan inverse of, this is 0 upon 4. So this will be 0 minus tan inverse of omega upon 2 minus tan inverse of omega upon 0 minus tan inverse of, this is omega by 10 and this will become 100 minus omega square upon 100. So we can cancel it and it will become 10 omega upon 100 minus omega square. Okay. Now, this tan inverse of 0 will be 0 degrees. Then tan inverse of omega upon 0, that is infinity. So, it will become minus 90 degrees. So, this is minus 90 minus tan inverse of omega upon 2 and minus tan inverse of 10 omega upon 100 minus omega square. Now, we can write it here. This is minus 90 degrees minus tan inverse of omega by 2 minus tan inverse of 10 omega upon 100 minus omega square. Now we are going to take different values of omega, and for those values we will calculate the phase angle. So now we are going to make a table in which we will take different values of omega and then we will calculate the phase angle. So we are going to take 10 values of omega, like we will take 0, 0 0.1, 1, 2, 4. We have taken different values of omega, and now we are going to put these values in the phase angle equation which we have obtained, and then we will calculate the phase angle for the system. So first we will take omega equals to 0 in this. So minus 90 minus tan inverse of 0 minus tan inverse of 0. So our phase angle will be minus 90. So we will write here minus 90 degrees. Then 0 0.1. So it will be minus 90 minus tan inverse of 0 0.1 by 2 minus tan inverse of 10 into 0 0.1 upon 100 minus 0 0.1 square. So when we solve this, we will get the phase angle as minus 86.7 degrees. Similarly, we are going to put different values for omega and then we will calculate the phase angle. I'm directly writing the values here. So for omega equals to 1, we will have here now omega equals to infinity. So omega equals to infinity, if we put here, then minus 90 minus tan inverse of infinity minus tan inverse of infinity. So it is going to become minus 90 and minus 90. So it is becoming minus 180 degree here. Okay. So if we take here, we have calculated for different values of omega the phase angles. Now we are going to use this table and the table which we have made for the magnitude plot to plot a Bode plot of the system. So now Bode plot, it is the logarithmic plot of the magnitude versus the frequency. So for Bode plot, we are going to use a semi-log graph paper, and in this semi-log graph paper, I'm showing you here. On the y-axis, we are going to plot the magnitude and the phase angles. The magnitude, it is in dBs, that is decibels, and phase angle, it is in degrees. Upper part will be the magnitude plot and lower part will have the phase plot. And on the x-axis, we are going to take the frequency, which is in radians per second. Now the divisions in the logarithmic plot, it is in the powers of 10. You can see here we will have 10 raised to the power minus 1, that is 0.1. Then 10 raised to the power 0, so 1. Then 10, 100, 1000. So in this way the frequency is changing. That is in decades of 10, that is in powers of 10, the frequency is changing. So this is a semi-log graph paper. Okay. Now the magnitude, it is always plotted with respect to the 0 dB line. Okay, 0 dB is taken as the reference line, and in case of phase plot, the minus 180 degree line is just taken as the reference line. So here I am going to first make the 0 dB line and then the minus 180 degree line, and according to our question, the values which we require, we can adjust the scale of the magnitude and the phase angle. So now here I am first making the 0 dB line here. Okay. This line I have taken as the 0 dB line. Okay. And the remaining scale I am choosing it as 10. Okay. So this upper half of the graph paper, it is our magnitude plot, and it is the magnitude in decibels I am showing here, and this black line, it is the 0 dB reference line. Okay. Now we will use the table for the magnitude. So our first factor is 20 log 4, that is 12 dBs, and it is having slope 0 dBs per decade, and it is a straight line of slope 0 dBs starting from point 12 dB. So 10 dBs I have marked here, so 12 dBs will be somewhat upper from this point, and I will draw a straight line having slope 0 dBs here. This is 12 dB point having slope 0 dBs per decade. Now our next factor is 20 log under root of 1 plus 0.5 omega square. It has the corner frequency 2 and slope is plus 20 dB per decade. So it will start from omega equals to 2 and slope will be plus 20. So this is 0 0.1, this is 1, this is 10, 100, 1000. This x-axis is showing the frequency. So this is 1, so this point will be omega equals to 2. So from omega equals to 2, we will have a line which is having slope plus 20. So it will be in upper side. Okay. So this is in upper side plus 20 per decade. Okay. Now we have the third factor, which is minus 20 log omega. So this will have the no corner frequency passing through omega equals to 1 and minus 20 dBs per decade is the slope. So it will start from 20 dBs. This is omega equals to 1 and it will have slope minus 20 dBs per decade. Now last factor is this. It has the corner frequency 10 and slope is minus 40 dBs per decade. So it will start from omega equals to 10 and slope is minus 40. This is omega equals to 10, this point, and slope is minus 40. So it will be somewhat more tilted. So we were having 4 terms in the transfer function, and for all the 4 terms we have drawn the magnitude plot. Now the resultant magnitude plot will be the combination of all these fours. That is, all the four graphs we have to add, and then we will get the resultant magnitude plot. So we will start from this point. This is 20 dB, this is 12 dB. So 20 dBs per 12 dB plus 12 dB, it is equal to 32 dBs. So the resultant magnitude will be 32. That is this point. So 20 plus 12, it is 32 dB. So we will start from this point. Now slope will be, due to this factor we have the slope 0 dBs per decade, and due to this factor we have minus 20 dBs per decade. So the total slope will be 0 minus 20. So it will be minus 20 dBs per decade till omega equals to 2. Because after omega equals to 2, this third factor has been added. So till omega equals to 2, we will have minus 20 dBs per decade. This point is 32 dBs and slope is minus 20 dBs per decade. Now, after omega equals to 2, we have this point. Okay, so we will have to add the slope, that is minus 20 was up till omega equals to 2. After this we will have plus 20, so minus 20 plus 20, it will be 0 dBs. So from omega equals to 2 till omega equals to 10, we will have the slope as 0 dBs per decade. Now after omega equals to 10, this minus 20, this minus 40 dBs per decade will be added in the slope. So 0 and minus 40 will be minus 40 dBs per decade. So this will be like this. Okay. So here slope was minus 20 dB. Here slope is 0 dBs per decade. And here the slope is minus 40 dBs per decade. So this is our resultant magnitude plot. I will show it by the red line so it will be clear to you. So this is our resultant magnitude plot. Now for phase plot, we will have to use that phase table where we have calculated the phase angle for different values of omega. Now if we see the phase angles, all the angles are less than minus 180 degrees. So we will draw the minus 180 degree line in the lower part. Okay, so we will have here this is minus 180 degrees. Then we will draw the scale. Now for different values of frequency, we will mark the phase angles. So for omega equals to 0, we have 90 degree. Okay, for omega equals to 0 0.1, we have minus 86.7 degrees. So minus 86.7 will be here. Minus 86.7 degrees. Then for omega equals to 1, we have minus 67.6 degrees. So this is 1 minus 67 will be here. Then we will have at omega equals to 2 minus 56.5 degrees. So at omega equals to 2 minus 56.5 degrees. Omega equals to 4, 52 degrees. So 2, 3, 4, 52. Omega equals to 10 minus 109. So 10 minus 109 will be here. Omega equals to 13 minus 126. So 11, 12, 13, and it is minus 126. Omega equals to 40, it is minus 168. So it is 10, 20, 30, 40, 50, 60, 20, 30, 40. So here we will have the magnitude as minus 168 degrees. Then minus 180 for infinity. So we are going to join all these points. So this is our phase plot. Okay. So in the upper half of the graph paper, we have plot the magnitude. And in the lower half, we have plot the phase angle. So the magnitude and phase plot together, they form the Bode plot of the system. So whenever we want to draw the Bode plot for a system whose open loop transfer function is given to us, first put S equals to j omega in the transfer function to obtain g j omega, and then calculate the magnitude, then logarithm of the magnitude, and then the phase angle. Form the tables for the magnitude and the phase angle, and using those tables you can draw the magnitude and the phase plot. First draw the magnitude plot for all the factors, and then draw the resultant magnitude plot, and then using the phase angles mark the points and then join these points to form the phase plot. So the magnitude plot and phase plot versus the frequency is the Bode plot of the system. So I hope that you have understood this problem, and in future you can solve the problems which are related to it. Thank you.